We looked at a couple exponential models yesterday. Now we're going to write our own based on different criteria. So we have our exponential growth and exponential decay, which grow and decay by the same percent. When we first looked at the graphs of the exponential models, we found that as x increases by 1 unit, depending on the base, there was a multiplication. So if our base was 2, then every preceding y value was 2 times as large. If our base was 4, it was 4 times as large. If our base was 1/2, it was half as large. So it's a multiplication factor or a percent of the change over time. And when we looked at the word problems, we saw a common theme of rate, which is represented as a percent. So exponential growth and decay show percentage of change over time, and it's a consistent percentage. Again, if that base is a value that's greater than 1, that's where we get our growth in most cases. And when the base is between 0 and 1, that's when we get a decay. Now, keep in mind, those will change as we apply transformations. So if I have a growth equation, but then I reflect it across the y-axis, well, then that becomes a decay equation. Okay, so there's some transformations that can adjust that a little bit. It just depends on the context that we're looking at. But generally speaking, if b is greater than 1, we have a growth. If b is between 0 and 1, it's going to be a decay. So that y-axis reflection can change the growth and decay. And then an x-axis reflection, it still is measured as growth or decay, but we call it a negative growth or a negative decay. Okay. So being able to identify based on the formula whether we're going to have growth or decay by looking at the base and identifying whether or not we have any reflections is going to be important. So if I have y equals 3 to the x, is that a growth or is that a decay? That is a growth. Growth, because our base is greater than 1. Our base is 3. For the second one, 1.25, is that growth or decay? That is growth again, because it's still greater than 1. All right, what do we think about y? That's decay. The base is greater than 1, but we have a y-axis reflection. And remember, yesterday we talked about the radioactive decay, the equation. This base is greater than 1, but that negative exponent is causing a y-axis reflection, turning it into a decay problem. So we have decay. All right, 0.5 to the x. It is also decay because b is less than 1, but it is, that's backwards. That is backwards by a lot, okay? So b is between 0 and 1, so we have decay. All right, and then what about 0.5 to the negative x? That's going to be growth. So the 0.5 starts the graph doing this, but then we have the y-axis reflection that flips it around, and it actually ends up being growth. Okay. Now, every formula or every exponential growth and decay is essentially based off of this formula to start. So we have a times 1 plus or minus r raised to the x power. What do you think the plus or minus refers to? When do you think we're going to use plus versus minus? Growth versus decay. If I have a growth, I will probably use plus. And if I have a decay, I will probably use minus, right? And remember that R represents rate. It is a percent of change. So what does 1 represent in that context? Why are we starting at 1? What does 1 represent?
Because you always start on 0, 1.
We do always start on 0, 1, but in the context, that whole thing creates our b value. In the context of rate and percentages, what does 1 represent? In the context of rates and percentages, what is 1? 100%. We start with 100% of a thing. Okay? So we start at 1, which is 100%, and then we are adding a percentage to increase it or subtracting a percentage to decrease it, okay, to get a decay. So we're starting with 100%, and then we are adding or subtracting other percents. Okay, we are adding or subtracting other percents to get the growth or the decay. Now, this A value represents our initial amount. Okay, that A represents our initial amount. How much are we starting with the thing? So let's look at some of our models from yesterday again. Okay, we see that we had an initial amount of 400. There's our A value. We talked about how that 29% is hidden in part of that 0.71. 1 minus 0.29 gives me 0.71. So there's my B value for my rate. We have A as our initial amount. We started out with 100 grams. And then even within our compounding interest formula, we have our initial amount. Now, albeit our rate of change is a little more complex with compound interest, but it's essentially the same idea. We're starting with 100% and then we are adding a growth rate. Okay, so all of these models follow this same general formula. An initial amount times whatever our growth factor is, raised to the power of x, and x is going to be whatever intervals that we're dealing with. Okay? All right, so we want to model growth and decay. So in 2009, we've got a town. They had a population of 15,500. Okay, 15,500 and consistently increasing by 10% per year. If this yearly increase continues, we want to predict the city's population in the year 2029, and we want to round to the nearest whole number because we're not going to have a part of a person. That would be a little ridiculous, right? So, looking at our formula, are we going to have growth or decay? Growth. So what formula are we going to use specifically? There you go. Make sure you're converting it into a decimal notation, okay? So we're going to use the growth. Amount of years, okay? So our initial amount is 15,500, okay? 1 plus our rate, which is 10%, so 0.1. And then we want to know the population in 2029, which is 10 or 20 years after 2009. So we would use 20 for our value of x. So that is our model to start. Once we have that, we can simplify it. So it would be 15,500, 1.1 to the power of 20, and then we can evaluate. 104,227. Okay, round to the nearest whole number. So in 2029, we can predict that they're going to have 104,276 people. Yeah. You would round, in this kind of situation, you would just round to the nearest whole. Because it's an estimate anyway. We're predicting what the population would be.
Is that the population of that city?
I don't know if there's actually a city named Lacombe. That's why it says, let's suppose. Larf Golf Club holds a single tournament every year. At the start of the tournament for a particular year, there are 512 players. After each round, half the players are eliminated. How many players remain after 6 rounds? So are we using growth or decay? Decay. Yeah, okay. I had to process all that part. Because I want you to be able to do exponential growth and decay modeling. It's the models. And these are, well, so it's eliminated by half. So it's 50%. right? So 0.5. And x would be 6, okay? These types of models show up a lot on the SAT. The exponential growth and decay, being able to recognize the difference between exponential growth and decay versus linear growth and decay, and identifying even this growth value. So for example, you could be given an equation like this, as well as a few other options, and it simply says which one of these represents a decay of 50%, okay? Or an equation like this, as well as some others, and would say which one of these represents an exponential growth of 10%. Okay, so these types of problems show up a lot. It's more important about the modeling than the actual solution part. So if I'm cutting it in half, what's the half as a percentage? 0.5, right? So 1 minus 0.5 gives me 0.5. All right? So after 6 rounds, we have 8 people left. Okay? All right, so we've got exponential decay with half-life. However, half-life is going to be slightly different, but we'll talk about that in a minute, just dealing with the time interval, okay? So first we're going to start with y equals, so we got a, and then we still have 1 minus our rate to the power of x. What is our value of a? We've got 400. So y equals, we start with 400 pounds of this thing. 1 minus rate. So if I'm doing half-life, what do we think the rate's going to be? 0.5. It's 50%. Half-life is how long it takes for half of the material to decay. So 50% of it. So we are going, half-life is always going to be 0.5 for the most part, okay, when we're dealing with half-life. It's decay. It's half-life. Half-life is always decay. So the value for the exponent, the time interval, okay, with half-life is a little bit different because it's half-life isn't really measured in years. They all have their own kind of half-life. So what we do is we take whatever that time quantity is, okay, whether we're measuring in years and months and days and hours, whatever the half-life is measured in, we take that time quantity, in this case, years, okay, the total number of years, and then we divide that by the half-life. Okay, so this is, actually, let me rewrite that. Let me just say total time. Total time divided by the half-life, okay? So if the half-life is measured in hours, you would take the total number of hours divided by the half-life. If it's measured in years, you would take the total number of years and divide it by the half-life. If it's measured in days, you would take the total number of days and divide it by the half-life. So whatever the half-life is measured in, different radioactive material has different amounts of half-lives, anywhere from fractions of a second up to millions of years, depending on whatever the thing is, okay? So here, our value for x, our total time is 72 years, and we want to divide it by the half-life of 15. So that is our exponent, 72 over 15. And we're going to round that to the nearest tenth of a pound. I think so. Oh, not 2.4. 14.4. 14.4.
Yeah.
Yeah. Oh, I thought you said 2.4. I remember the 0.4, and that sounded good. Yeah. So we get approximately 14.4 pounds remaining after 72 years. Okay?